All right, so next what I want to do is I want to think about some linear transformations and some of the different properties that these linear transformations have. So let's keep talking about transformations from R2 to R2, and of course we're going to keep talking about linear transformations from R2 to R2. And I want to emphasize that in a certain sense, the only thing we've been talking about all semester are linear transformations. Okay, so everything that we've been doing so far has really come down to just understanding linear transformations. Now, of course, at first we didn't talk about linear transformations at all until just very recently, but linear transformations are really the kind of big picture, top of the mountain view that once you have that picture of linear algebra, everything starts to click a little bit more. So linear transformations are really the heart of linear algebra. And that's why I wanted to do this next. So that's why I wanted to talk about linear transformations as soon as I did. So we'll talk about general linear transformations from a vector space V to a vector space W in a second. But for now, what I want to do is I want to talk about some different properties of linear transformations, specifically linear transformations from R2 to R2. So what I want to do is I want to think about taking some linear transformation T, and I'm just going to write this in the old way, so without a matrix, although it's clear what matrix there would be. But let's say that we're going to send this to the matrix 4, 1, 3, 1. Okay, and I just lied to you. I just said I wasn't going to write this as a matrix, and I did it anyways. Let's write this as, 4x plus y, 3x plus y, which you can also think of as 4, 1, 3, 1 times the vector xy. Either viewpoint is perfectly fine. I'm just going to stick to the first one for now. What I want to know is I want to find all the vectors. So I want to find all the vectors, say x, y, so that when I apply the linear transformation of those vectors, what we get is the 0 vector. We get 0, 0. Right? So I want to figure out what are the vectors that get mapped to the origin. And of course, that's going to depend on the transformation, right? We saw previously that you can have a transformation where everything gets mapped to the 0 vector. Or you can have a transformation where some things get mapped to the 0 vector lots of times, or you can have a linear transformation where it's always going to be the case that there's always at least one vector that gets mapped to 0, namely the 0 vector. So I think it's actually important enough. I just want to point out, let's call this a proposition. I just want to point out that if T going from R2 to R2 is linear, then T of the vector 0, 0 has to be 0, 0. And there's lots of ways to prove this, but I think the easiest is just to walk through the definition of linear. So by linearity of T, T of 0, 0, I can write 0, 0 as 0, 0 plus itself, right? That's the same as T of 0, 0. So just by linearity of T, I can write T of 0, 0 as, again, T of 0, 0 plus 0, 0. And by linearity, this is T of 0, 0 plus T of 0, 0. And now think about what's happening here is I have some quantity, I don't care what you call it Z, I don't care. But you have some quantity Z, where Z is equal to Z plus Z. Okay, so we have that this quantity is equal to itself plus itself. And the only way that that can happen is that implies that that quantity must be the 0 vector. So this implies that T of 0, 0 is equal to, let me just write this one more step just to be perfectly clear about what I'm saying. This is t of 0, 0 is t of 0, 0 plus t of 0, 0. And if I subtract t of 0, 0 from both sides, what I'm going to get is, on the right side, I'll get this other term, which is t of 0, 0. On the left, I get, remember that this output is a vector in R2. I'm subtracting itself, so I get the 0 vector in R2. And so there we go. So it turns out that the 0 vector always gets mapped to the 0 vector for any linear transformation. This is actually true for any linear transformation at all, regardless of whether it's between R2 and R2 or between polynomials and matrices. It doesn't matter. Every linear transformation satisfies that same property. So that's why when we initially started talking about linear transformation, so that was last week, so that was March 12th when we were still in class on campus, I said that a linear transformation has two properties. The first is that it sends lines to lines. So you can think about geometrically, why does a linear transformation have to send lines to lines? But the second is that it fixed the origin. The fixing the origin part turned out to be completely crucial to being a linear operator. Okay, so that's the first thing. So let's go back. Remember that this was all kind of a tangent to our original question of we were studying this linear transformation. We wanted to find all the vectors x, y that get mapped to the 0 vector. And of course, what this really means is we want to find all the vectors x, y, so that 4x plus y is 0 and 3x plus y is 0. We're back to solving two equations, two unknowns. We know exactly how to do that. We know lots of details on how to do that. In fact, we know some pretty fancy things about how to do that. What we're really doing when I ask for finding the vectors, when I ask you to find the vectors x, y, so that t of x, y gets mapped to the 0 vector, I'm really asking for what's the null space of our matrix 4, 1, 3, 1. So really we need to find the null space of the vector 4, 1, 3, 1. And since the determinant of the matrix 4, 1, 3, 1 is not 0, that means that the rank of 4, 1, 3, 1 is 2. It's got full rank. It's invertible. And hence, the nullity, the dimension of the null space of the matrix 4, 1, 3, 1 is 0. So that means that the null space 4, 1, 3, 1 is a zero-dimensional subspace. In other words, just the 0 vector. Okay, it's that single vector. Okay, that turns out to be the only vector in the null space. Okay, and so so we can talk about the null space of a matrix, but in relation to a linear operator, this is what's called the kernel. Okay, so the kernel of T, denoted ker T. In fact, let me write this on the next page. So let me write this on the next page. The kernel of T is going to be the set of vectors. Let's just, again, for now, let's say T is still going to be a linear transformation from R2 to R2. But this is going to be the set of vectors V, so that T of V is the 0 vector. Okay, and this happens to be the case that the kernel of T for these particular transformations, this is not true in general, just as a fair warning here, this is only true for transformations from Rn to Rm, right? It's only transformations between different dimensional vector spaces over the reals, but kernel of T is going to turn out to be the null space of A, where T, V is given by AV. Okay, so the kernel turns out to be the null space of A. The kernel, though, is defined for all sorts of linear operators, regardless of whether we're going from R2 to R5 or matrices to polynomials or whatever your vector spaces are. The kernel is going to be defined on those. And so what I want to do is I want to prove a few things. I want to prove that if T goes from R2 to R2, again, just to keep this perfectly straightforward, then the kernel of T, so then the kernel of T is a subspace of R2. And we'll do this in general next time, but just for now, the kernel of T is a subspace of R2. And to prove that something is a subspace of R2, we just have to prove that if, say, U and V are in kernel, or in the kernel of T, then U plus V is in the kernel of T. And now we need to show that if C is a real number and V is a vector that's in the kernel of T, then CV is in the kernel of T. By the way, what I mean when I say if is that if this is the case, then that suffices in showing that the kernel is a subspace. So we have these two things to check. Okay, we have that the kernel is closed under addition, and we have that the kernel is closed under scalar multiplication, and if that's the case, that'll show that the kernel is a subspace of our domain, R2. And so let's just let U and V be in the kernel. Again, I'm not assuming anything about T other than the fact that it's linear. Then what does that mean other than to say that T of U is the zero vector and T of V is the zero vector? And hence, by linearity, T of U plus T of V is the zero vector plus the zero vector, better known as the zero vector. Okay, so that's the first thing. The second criteria is let's let C be a real number, V a vector in the kernel of T, and then, of course, since it's in the kernel, that means that T of V is 0, and therefore T of CV is going to be C times T of V by homogeneity of the linear operator. T of V is 0. Any constant times the zero vector is the zero vector. Okay, so this tells us that so U plus V is in the kernel, and C times V is in the kernel. So in other words, the kernel is a subspace of our input, our domain R2.